Hey Geometry, so today we're going to get into 7.4 parallel lines and proportional parts, so staying kind of within triangle similarity, some more properties and things that we observe within these. So if a line is parallel to one side, parallel to one side of a triangle and intersects the other two sides, then it divides the sides, or splits, into segments of proportional length. So here's my parallel line there that intersects the two sides of the triangle. It's parallel to one side, intersects the other two. It's going to split those into proportional lengths. And sometimes we call this the side splitter theorem. A little easier to remember maybe than the triangle proportionality theorem. So we call it side splitter, and I'm fine if you just want to call it that. So for example, if BE here is parallel to CD, then AB over BC is going to be equal to AE over ED. AE over ED. So it splits those sides into proportional. This proportion matches this proportion. So applying that down here, in triangle PQR, we know that ST is parallel to QR. And then if PT is 7.5 and TQ is 3, then an SR down here is 2.5. They want us to figure out what PS is, figure out what that proportion is. And so since these are parallel lines, we can use that side splitter theorem to know these parts are proportional. We could say x over 2.5 equals 7.5 over 3. And we could cross multiply. 3x is equal to whatever 2.5 times, I don't know where I got 7.3 from. 2.5 times 7.5. 2.5 times 7.5 is 18.75. And divide that by 3, which is 6.25. So x is 6.25. 6.25. All right, in the next one, we're using the same thing. You could try this on your own first and see if you get the same answer I do if you want to pause. PS, I'm just going to change color here, and since it's going to be on top of the same figure. So PS is 12.5, SR is 5, and that ratio should match PT, which is 15, to TQ. So I'll call that one X. And so we could set up a similar 12.5 over 5 is equal to 15 over X. We cross multiply, we get 12.5X is equal to 5 times 15, which is 75. 75 divided by 12.5 is a nice 6. So X is 6 in that case. All right, this thing works in reverse as well, the converse of the triangle proportionality theorem. If a line divides two sides of a triangle and separates the sides into proportional corresponding segments, then the line is parallel. So up here we know if it's parallel, then it's going to divide those sides into proportional parts. Here, if they're proportional parts, then we know it's parallel. So for example, if AE over EB, so they did little over, this part over that part, and it works both ways. You can always flip these proportions, is equal to CD over DB, then we know that ED is parallel to AC. That's what we know. All right, so here we're supposed to check that if triangle DEF, the bigger triangle here, if EH is 3 and HF is 9, and DG is 1/3 the length of GF. So they don't actually give us those lengths, but they do say this is 1/3 of that, which matches this. This is 1/3. Then we know the sides are proportional. Another way we could say this, we could say that this side is equal to 1/3 GF, and so we could set up a 1/3 GF over GF, and then what we see is that it cancels and we just get 1/3 is equal to 3/9. And so yeah, 1/3 does equal 3/9. Therefore, we know that GH is parallel to DE. Using the converse of the triangle proportionality theorem, you can also say converse of the side splitter theorem. All right, moving on. A midsegment of a triangle is a segment with midpoints of two sides of the triangle. So we go to the midpoint here. Notice AB, these parts are marked as congruent. P is the midpoint. And so a segment that ends at two of the midpoints is a midsegment. So every triangle has three midsegments. We see them there. The midsegments are, in this case, RP, PQ, and RQ. Those are our three mid-segments of that triangle. So we got a mid-segment theorem. A mid-segment of a triangle is parallel to one side of the triangle, and its length is 1/2 the length of that side. So this mid-segment here, it goes to the midpoint of GH and FH. It's, those are the two midpoints. It's parallel to that other side, and it's also going to be exactly 1/2 of that. The ratio here of this length to that length is 1:2. So this side to that side is 1:2. So we can apply that to some of these problems here. If XY and XZ, so both of these segments are mid-segments of triangle RST, find each measure. So they want us to find XZ. Well, we know that this XZ is going to be parallel to this side, but we also know that this segment is going to be half of that side. So XZ is equal to 1/2 of 13, which is 6.5. ST, well, I know that this is a mid-segment, and then it's going to be half of that one, so I could say that 7 is equal to 1/2 of ST, and then just solve for ST. Divide by 1/2, which is the same thing as multiplying by 2, and so we get ST is 14. It's going to be double that length. And then finally, RYX, we want to know that angle there. Well, it turns out that the mid segments are parallel. So this segment's parallel to that segment. And so these could actually be marked as congruent because they are alternate interior angles. And so it's just going to end up being exactly the same, 124 degrees. Is that angle there? It'll be there. Another special case of the triangle proportionality theorem involves 3 or more parallel lines cut by 2 transversals. So I've got my 3 parallel lines down here. Oh, out of focus. Sorry about that. Hopefully that's a little bit better. Looks like it's all right. Yeah, there are my 3 parallel lines cut by my 2 transversals. Notice if transversal A and B are extended, then they form triangles with the 3 parallel lines. So like there's a triangle here. If we extend this out, that triangle is going to be similar to this triangle, which is going to be similar to that triangle. All right, so we'll continue for that. All right, so proportional parts of parallel lines. If 3 or more parallel lines intersect 2 transversals, then they cut off the transversals proportionally. So for example, in this case, if AE is parallel to BF, parallel to CG, so those are my 3 parallel lines, then AB, this segment over BC, or CB, this segment over that one, we can label, I guess, in either direction, is going to be equal to EF, this top part, over FG. And so we can use that, and that relates to triangle similarity, so we can use that to solve various problems such as this one. Megan is drawing a hallway in 1-point perspective. She uses the guidelines shown to draw the 2 windows on the left walls. If segments AD there is parallel to BC and WZ and XY, all those segments are parallel, and AB is 8 centimeters and DC is 9 centimeters. and zy is 5 centimeters, what would wx be? So these little parts in between those are going to be proportional. So I'll just call that x. We can set up 8 over x is equal to 9. And I'm kind of going left to right, 9 over 5, but you could have done this in other ways. Cross multiply, we get 9x equals 40. Divide both sides by 9, you get 40/9, or, I mean, then that doesn't reduce, whatever that is, and is a decimal, 4.4 repeating. All right, and then what if those parts are instead of being similar? What if those parallel lines are, and those parts are congruent? So if 3 or more parallel lines cut off congruent segments on one transversal, so if they're cutting off congruent segments on one of the transversals, then they cut off congruent segments on every transversal. So these parts here would also be congruent. So if they're all parallel and AB is congruent to BC, then EF is congruent to FG. EF is congruent to FG. And so we can use that here. In this thing, we got our 3 parallel lines cutting a couple transversals. And if there was a third transversal, those parts would be congruent as well. Since these parts are congruent, we know these parts are congruent. And so we can set up and solve a couple of these. 3y plus 8 I know is the same as 5y minus 7. So equals 5y minus 7, which we can solve. 3y minus 3y plus 7 plus 7. So we get 15 is equal to 2y divided by 2. And y is 7.5. So that's what y would be. X, we can do something similar. 6x minus 5 we know is going to be congruent to 4x plus 3, or equal to that length. So we subtract 4x on both sides, minus 4x plus 5. That's gone, that's gone. We're left with 2x is 8, and x is 4.